Howdy, welcome to Computer Graphics, Animation, and Simulation. Today we're going to talk about fluid simulation. To do that, we're going to talk about these four main topics: Lagrangian versus Eulerian simulation, mathematical background, some important things we need to know, the Navier-Stokes equations, and potential field flows. So Lagrangian and Eulerian approaches to simulation can be compared more or less in how you implement them. So with Lagrangian, we try to treat everything as a discrete element. In other words, they're just individual particles or something. So it means we need to track the motion individually, and essentially we can simulate some nice complex things like tornadoes and different kinds of things because the particles don't have to be fixed in a certain spot. And if you're familiar with particle systems or rigid bodies, the concept is similar. Now with Eulerian, what we want to do is use concrete cells. We divide everything into some sort of lattice. That's one example, or maybe we place the Lagrangian particles at specific spots in space, and they are not allowed to move. And the idea is that we want to simulate the flow between the cells. So rather than try to track pairs of Lagrangian elements, we know where everything is, so it's easier to keep it consistent. And because it's more consistent, it's typically easier to do. However, it may turn out to be less flexible in terms of it's more coarse. So Lagrangian, we can think of it as a bunch of particles that we're simulating the interaction between, and Eulerian, we're basically using concrete cells that we're simulating flow between the cells. So regardless of whether you use a Lagrangian or Eulerian approach, there are certain mathematical concepts that are not going to change for either one of them. So let's take a look at those. First of all, we need to be familiar with the idea of a field. This is essentially a function that everywhere in space has some definition. In other words, if you think of the cells, each of them has a value. So this is a spatial idea. So we might say that we have a function f of x, and that x is a vector. Say we're doing 3D, so we have x, y, and z. But we can also have time-varying fields as well, and those will be f of x and t. So we include a time component. This, of course, will make the simulation more complex to deal with, but that's a reality. So we have some notation. So we might say that a scalar field, we'll use phi of x to represent a scalar field. And scalar fields, an example of that would be like pressure. Pressure doesn't have an idea of direction associated with it. However, we do want to look at vector fields as well. Say u of x will be our notation there. An example would be velocity. So what is a fluid velocity? That does have direction associated with it. In order to understand these, we need to think about some differential operators, and these are going to allow us to interact with these fields. The first one is called the gradient. The second one is called the divergence operator. The third one is the curl operator, and the last one is the Laplacian operator. So let's talk about the gradient operator. Here we have this upside down delta symbol, which we call del. Sometimes it's called the nabla symbol. And we have our scalar field, phi of x, and we want to calculate the gradient. Well, what we do is we take our function and we take the derivative with respect to x, respect to y, respect to z, because we're working in 3 dimensions. And so, as an example, let's say we have a function f of x equals ax plus by plus cz. Well, we want to find out what the gradient is. So in order to compute this, we will first start with the first element, which is take the derivative with respect to x. And in order to do this, we basically treat the other elements in our equation, or terms in our equation, that don't have x's as constants. And so essentially those will end up being 0 because the derivative of a constant is 0. And then we have the derivative of ax is simply a. And we can do this the same for the other ones. So the derivative of f of x with respect to y is then b, and the same thing for the derivative with respect to z, which is c. So the gradient is not so bad. So now let's look at the divergence operator. So this almost looks like the gradient dot product with u, although it's not really a dot product, but the concept is similar. So essentially what we have is we're taking the partial derivatives with respect to x, but we want to do that on the components of u. So what happens is that we end up taking the partial derivative of u of x with respect to x, then we add the partial derivative of u of y with respect to y, and then we take the partial derivative of u of z with respect to z. So you can see that the idea behind the dot product is evident here, although we're not just simply multiplying u of x times the partial derivative. So the reason we would like to do this is we might have a vector field that we want to convert into a scalar field. And you can see that this does that. We have a scalar as an output for this divergence operator. For fluids, we might want to find out how is this vector u expanding locally. And this is a important concept. Sometimes we want to use this as a constraint. For example, if we're talking about fluids, we might want the divergence for the entire vector field to be 0 for incompressibility. So even though all the small elements of our simulation might not be 0, individually, collectively as a whole, we would say this is a constraint. The entire divergence of the entire field has to be 0. The curl operator has the idea of rotation, and you'll notice that we have the nabla symbol and the cross product symbol with u. So the idea of the cross product is going to be evident in the way that we calculate this operator. In fact, we see that when we do this operation, that it is basically the cross product, except that instead of just like before, we don't just multiply the values. We're actually talking about derivatives here. So the first element would be the derivative of u of z with respect to y minus the derivative of uy with respect to z. Then the second element, derivative of u of x with respect to z minus derivative of uz with respect to x. And then lastly, the derivative of uy with respect to x minus the derivative of u of x with respect to y. And this basically represents rotation. So if we don't want our fluid to have any kind of rotation at all, we would just say this has to be 0. And a good way of thinking about this is to imagine a ball rotating on top of a fluid. So let's just say the fluid doesn't have any movement at all, but there is some rotation. So you can just kind of imagine a ball just kind of circling around rather than moving around on top of a water. And sometimes you have movement associated with it, but if you've ever seen an object rotating on the water, then this is what is happening. And the last operator we're going to talk about is the Laplacian operator. So here we have the nabla squared, and essentially what we're doing is this is going to correspond to a double derivative. So in order to do this, we just, same idea of using the dot product before, we're going to get the sum of the second derivatives with respect to x, with respect to y, and with respect to z, and we take the sum of those together. So we can do this with scalar fields, and we can do this with vector fields. So with scalar fields, we have our function phi, and we're basically just going to apply the second derivative of phi with respect to x, add the second derivative of phi with respect to y, and add the second derivative of phi with respect to z. One well-known example of this is the heat equation, where the derivative of phi with respect to time equals alpha times the Laplacian of phi, where alpha is the rate of diffusion. So this is a very, basically just kind of says that the change in your function is the product of whatever diffusion amount is with the Laplacian. Okay, so we can also apply the Laplacian to vector fields. So let's say we have our function u, which is we're looking at 3 dimensions right now, so it's got ux, uy, and uz, and essentially we just apply the second derivatives with respect to each one of the components. And the way that this is going to look, if we were to calculate this out, we'll do the first element. So we'll have the first derivative of ux with respect to x, or I guess the second derivative, and then we'll take the second derivative of ux with respect to y. So now we're ready to look at the Navier-Stokes equations. So the way that this is set up is we have the density times the change of velocity, the change of rate of velocity, and that's going to be equal to the negative gradient of pressure, and then we have the addition of the viscosity of the fluid and some external force. Okay, so we have the change of rate of the fluid velocity field. We have the pressure gradient. In other words, how is the pressure changing as the fluid is moving around? A change in pressure does imply a change in velocity. And then we have the viscosity. So this eta term is, there's a lot of physical constants for eta, and that is going to affect how thick or runny the fluid is going to be. So is this water or is this like corn syrup? And then lastly, we have the external force. So we might have external forces acting upon our fluid. Now, we normally imply a constraint. So we might say that the divergence of u equals 0. And in order to think about this, we have to remember this is for the entire field as a whole and not every individual cell. Individual cells may have the diverging velocity, but on the whole, it's not changing. What this means is that it's incompressible. So your fluid might be moving, changing, however, it's not being compressed. Now, you can take this constraint away if you're talking about gases, but most of the time we're not trying to simulate a gas, we're trying to simulate some kind of fluid like water. Now, as our equation stands, it's not very usable. And the reason for that is that it's defined in newtons per meters cubed. So, if we're doing physical simulation, it's a lot easier to deal with acceleration. So we need to figure out how do we get there. All right. So one of the first steps that we can do is we can divide through by the density. All right. So that's one step. The second step is to understand this change of rate in the velocity field. And so in order to do that, we have to realize that this is not just a derivative of u with respect to time. It's a little bit more complicated than that. So first of all, we're going to have the acceleration, so dot u plus this second term, okay, u dot the gradient times the velocity. So if we expand this out, we'll see that we have the acceleration plus u of x times the partial derivative of u with respect to x, and so on. So what are these terms? So we mentioned the first one is the acceleration field. So how is the field changing? And then secondly, we have the convection term. So this is, if we remember, we talked about the heat equation. This has kind of got the same idea there. And the idea is that convection is how material is transported by the velocity. Okay, and then not to be confused with advection, which is the transport of the properties of the fluid. Okay, so now that we have this, we can transform our equation so that it's written in terms of the acceleration field. So we have the convection term minus the gradient, the pressure gradient, plus the viscosity, plus G. And now we can see that the we also want to keep in mind that we have our we have this constraint for our incompressible flow. So now that we have a basic understanding of the Navier-Stokes equation, let's talk about potential field flows. And essentially we're trying to make some assumptions about what the flow is doing, because if you noticed, this equation still looks pretty complicated and lots of questions are going to come up. Well, how do we actually handle this equation? So one of the things we can do is think about how can we simplify this fluid simulation. Okay, so first of all, we could say that the flow is steady. That means that instead of having u of x of t, in other words, it's changing in time, we're only dealing with u of x. In other words, the fluid does not change with time. Secondly, we might say, let's look at inviscid fluids. In other words, we set the viscosity to 0. In other words, we won't have any turbulence associated with this. This can help control the stability of the simulation, because turbulence can cause rapid changes of velocity that are hard to maintain consistency inside the fluid. This last one we've looked at, which is, let's make sure the fluid is incompressible. So the gradient is, or the divergence of the velocity is 0. So you would, if you're trying to do some kind of gas, this, of course, you cannot use, those are compressible. And then lastly, we could say maybe we could assume it's irrotational, so that the curl of the velocity field is 0. And what this allows us to do is say that instead of u being a vector field, it's actually going to be a scalar field. And there's three things that we can do if we make this assumption. One is we can look at a uniform type uniform flow. So we might say that our scalar field is a linear equation, ax plus by plus cz. And one way of thinking about this is our fluid is just flowing in one direction. Okay, second thing we could do is we could add sources or sinks. So maybe we have fluid coming from a location, or maybe we have a drain of some kind. So we could say that phi equals some constant a over 2 pi times the natural log of r, where r is the radius of the source or the sink. And so a source, essentially, if we were looking at a vector field, we would see that the velocity is going away from the source, and if it was a sink, we'll see the velocity is approaching the source. And lastly, we might want to do vortices. This is something we can do by setting phi equals to b over 2 pi times theta. And what this will let us do is essentially we can have the flow going around one of our points. So if you're thinking of the Eulerian method, these would be the cells and the fluid would be going around. So it's still got some rotation to it, but the rotation is not in a single point. All right, so that is some things that we can do to simplify the Navier-Stokes equations, and it makes it easier to do certain classes of fluid simulation. So let's go ahead and review. We were talking about the Lagrangian versus Eulerian simulation. We went over a mathematical background, including 4 differential operators: the gradient, the divergence operator, the curl operator, and the Laplacian. And then we took a look at the Navier-Stokes equations and turned it into a form that's a little bit more usable for us in computer graphics. And finally, we talked about potential field flows. In other words, can we make some assumptions about the flow? And we talked about being able to simulate uniform flow, sources, sinks, and vortices. Well, thank you for watching the video, and adios.